Yeah, so we're going to talk about a new compiler backend for Radv called ACO. Okay, that works nicely. So I'm Bas Nieuwenhuizen. I'm pretty much the maintainer of Radv these days since the start. And here's Daniel. He's been working for Valve in mostly getting this new compiler backend working. And today I'm going to give a short introduction at what the hell do we mean with a new compiler backend and why did we do it. Daniel's going to show you like a rough overview of how it works and some awesome things we can do with it. And then I'm going to give you some nice results of the effects it had. And basically, Radv is an independent Vulkan driver for AMD GPUs. We have pretty much very little AMD involvement at all. And Vulkan as a graphics API, like these days, a lot of the graphics API things like applications can specify shader programs that you can run on their GPU and that they can calculate things. And these days, these programs can actually get pretty complicated, and compiling them to work on their GPU nicely is really important for getting good performance as a driver. And one of the limitations here is that every GPU vendor has their own instruction set for the GPU. So it's not like on a desktop where you can say, hey, I'm compiling this when I'm releasing the software and then handing it off, but you really have pretty much a just-in-time compiler to compile those programs to work on the GPU, and that's in the driver. In Vulkan, most applications specify shader programs in SPIR-V, which is kind of an intermediate format. And then first thing we do in the Radv driver is parse that format and convert it to NIR, which is basically an intermediate format that is used by most Mesa drivers these days. It is pretty much our middle end IR, in which we do a lot of optimizations. We do linking between shader stages like vertex shaders, fragment shaders, and figuring out outputs and inputs. And then what we've historically done with Radv is mixing this into, putting this into LLVM. And then there's an LLVM backend that generates code that runs on these GPUs. LLVM internally has also like multiple intermediate representations, like it has its own middle end IR, and then we get to LLVM machine IR, which is the backend, and like does really have backend specific restrictions encoded. And we're basically saying like, okay, we don't want to compile with LLVM anymore. We're using a different backend. One of the things we're able to do is like NIR was already a middle end IR, so we're saying like we're only going to do a backend IR with all the lowering to make it work for our GPUs. And on the diagram you can basically see where that fits into our stack. And then the question is, of course, why did we do this? Because essentially LLVM, the compiler, the backend for AMD GPUs, gets pretty much worked on by people from AMD. So it's nice and like gets you a lot of stuff pretty much for free because other people are doing it. And I want to point out two big reasons why we started this. Basically, what triggered this is that in LLVM, we've had a lot of trouble with dealing with control flow. Like in GPUs, control flow doesn't tend to work exactly the same as your CPU programs, because in a GPU, we're typically executing multiple invocations of the program at the same time using SIMD, which means that we have to do basically all kinds of mangling in the control flow, like to go from control flow to predication and then other steps. And it turns out that basically a top issue for GPU hangs or performance issue with shaders in Radv was actually when we got control flow wrong. in first place. Like it's very easy to get some kind of an infinite loop or something when you do this wrong, or there are some other issues I'll explain a bit later. There's also compile time performance. Like I said, this is a just-in-time compiler and a lot of games basically compile their shaders really on demand. Like the typical model with DirectX and GL was that they try to compile their and how that ends up working is that they try to compile their shader the first time you're using them. Typically, compile times can end up being more than like a single frame of rendering, so you're getting stutter in your games, which like if you get a lot of stutter, your game experience is not going to be nice at all. And yeah, at some point we figured out like LLVM as a compiler was pretty slow, and we could make things much faster. And I basically want to go back to the control flow thing, where I'm going to give you an example why we need it. And to consider this is like if you think about SIMD and you can think about a CPU tool like SSE or AVX or whatever, you have like one register which basically is a vector of values. Let's call those vector registers. But sometimes you can say like, hey, all my values are the same in all my lanes or all my program invocations in this case. So I can basically decide not to use a vector register but a scalar register and do the instruction basically on one lane. And it turns out sometimes that's much faster. Sometimes it's even required by the instruction set because there's no way to do it with vector instructions. And this is actually been a pretty common restriction, so that like in SPIR-V, like in that initial representation that applications give the driver, there's actually rules like if you do images based on, have an array of images, like it all needs to be the same. And there is some tricky thing there because of course, whether your value is the same in all the lanes pretty much depends on what lanes are active in your predication. And that very much depends on your control flow. I take an example here, which is basically a short loop, and I do two texture accesses here. So one of the big examples where things need to be like the same in all lanes is which textures are you going to access, which is like the first argument in those texture instructions. And what this loop does is basically what we try to do is iteration I exits the loop in lane I. And how you would factorize this is in your control flow on the graphics card, you would basically loop to this as long as any lane is active at all, just in the loop still. And then there's actually two blocks here in which we have a texture, like there's the break block and the merge block, and these are executed different times. Like the break block is executed in the loop. So when, in this case, like every iteration, like one lane exits the loop. So that break block gets executed X number of times, while the block at the end only gets executed one time. And one obvious issue here is that, like in the loop, I is obviously the same for all the lanes that are still active. But outside of the loop, it's different because you exited a different iteration. So here, at the first location, the texture fetch is pretty much allowed. In the second one, not, because you're using these non-uniform accesses. However, let's look at how this would look at a control flow graph, like with basic blocks and everything. And you see that these two different blocks end up being like a single exit, single entry, and your first intuition for a compiler would be, hey, let's merge those. And in this case, that's totally not allowed because like they're executed at different times. And a big problem is for LVM, like we don't have any structured control flow. So we're just saying, hey, like this is only a basic block-based control flow graph, and we're throwing all that information away. And then, of course, the big problem gets to be, like, how do we figure it out again? Like, you can say, like, hey, there's two basic blocks, single exit, single entry. That's obviously going to come from an example like this, but as your control flow gets more complicated, reversing this from your example becomes harder. And near, basically, as on the left, like, it stores a graph of, like, what is my structured control flow besides the control flow graph, and you can really see that, and you can really use that to make a case by case, like, how do we want to lower this? And that really, like, just not throwing that information away helps a lot. And that's it for my motivation why to integrate better with near and why we thought it was a good idea. I'll let Daniel talk about the high-level overview of our new compiler backend.
Hello. So what I'm going to talk about is how does ACO work internally now? And we try to base ACO on modern compiler principles. So what does modern compiler principles mean? Well, basically that the concepts we are using are only 20 years old and not 40 years old. That is modern in compiler construction. A very small disclaimer. The concepts we are using, and despite being modern and very fancy and cool, are tailored towards the AMD microarchitecture. And this means they are not necessarily applicable to other microarchitectures. Just keep this in mind when you hear about other backends. Yeah, ACO is written in C++, okay. We have a divergence aware instruction selection, and we can directly use the near shader or the divergence analysis on the near shader to do the instruction selection, and therefore it can be much more aggressive. And we actually saw, yeah, that this worked quite nicely. Also, like Bas already said, on the control flow graph side of things, we maintain the logical control flow graph, which is basically just the near control flow graph, and also the linear control flow graph, which is the physical control flow graph, what the GPU in fact executes, so hardware-wise. By maintaining both, we have all information available, which is necessary to figure these kind of problems Bas just mentioned. Our IR is just the hardware instructions in SSA form enriched by a few pseudo operations, and we do SSA-based register allocation. I will get back to that. How do you? Yeah, would be cool to see it here as well. So our ACO starts pretty normal, like every backend, by instruction selection, translating from near to our IR. Then we do some small optimizations. I think that's also pretty normal, value numbering, instruction combining, these kind of things. We have to insert execution mask handling manually. Yeah, just a necessity of the GCN architecture. And then things get weird. Because we decided to do like everything differently. We already do spilling in this moment, which is pretty early. Normally, this is done at the same time as register allocation. So we do spill decisions this early in the pipeline. We afterwards schedule and then do register allocation, everything before SSA elimination. So translating out of SSA is done like at the very end. And then we only do some small lowerings and the assembly. So why do we do that? It is really uncommon. And the reason is the register pressure, or more register pressure control. High register pressure yeah, everyone knows that high register pressure might lead to spilling. Okay, and scheduling is a big part of increasing or decreasing register pressure. And on AMD GPUs, and as far as I know also on NVIDIA, the register file is shared between the hardware threads executed on the SIMD units. So this means a SIMD unit on AMD GCN GPUs has 256 vector registers, and these are divided among at most 10 hardware threads, or we call them waves. Yeah, this means the more registers your shader uses, the less parallelism you get. How do we solve this problem? Well, we do the SSA-based spilling and register allocation. SSA-based register allocation can guarantee that your shader will not use more registers than you previously computed on the IR. So in SSA, you can compute how much registers your shader will need, and the register allocator can guarantee that fact. It might need to insert some shuffling instructions, but it is always possible to find a register assignment which stays below these limits. And so the idea we had, well, that is quite some nice information if you already know beforehand how much registers you are going to use. So let's try to do the scheduling within these limits. So that scheduling, which normally increases the register limit, also can be bounded. Scheduling under register constraints normally is, or in the general case, is a computationally hard problem. You won't find a linear solution for that. And so we had to come up with something different, and I want to present you a small algorithm. Yeah, I hope you can read this. So this is how our IR looks like on the right-hand side. On the left-hand side, you see the register pressure we computed after executing each instruction. I think you don't have to understand what this is going. It's what this shader wants to do. It's just a pretty normal fragment shader, or rather the beginning of a normal fragment shader. And our scheduler now, instead of building a dependency graph and rescheduling all instructions, it's just looking for long latency instructions. And these are, yeah, well, basically only the memory loads, nothing else. So our scheduler walks forward through the shader until it finds the first memory load instruction, which is here, a load dword. Then we simply check the previous instruction. The previous instruction here, by the way, is just a 0 extension of the pointer the memory load is using. So the previous instruction, our memory load obviously depends on the previous instruction, so we cannot change the order of these two. So what we do is just checking the instruction before, just a different instruction. It seems to have no dependencies with our current instruction. And what we can do is we just rotate this thing and reorder them. You see on the left-hand side that the register pressure has changed. So our scheduler is able to compute the changes on the register pressure, and this means it can also stop scheduling in the moment the register pressure might exceed certain limits. We continue by just checking the next instruction coming before. It's also independent from the instruction we want to schedule, and move it down. You see that we keep the order of the instruction we schedule down. By keeping the order, we don't have to check any dependencies between these other instructions. Yeah, the same we do with the next instructions before that. We also move them down, always changing or adjusting the register pressure, and we stop when we encounter a p-logical start. That is just a pseudo instruction indicating that here actually begins the shader we translated from the near. And before that, it's only some things necessary to maintain the SSA or execution mask handling. So what we do when we are done in this direction, well, we can also check the other direction. If we look for the first user of the instruction, which here is an image instruction, so we obviously or apparently loaded some descriptor. And after the first user are maybe also other independent instructions which can be moved down so that we increase the distance between our load and the first user of the load. So when done with this, when the scheduler decides that the distance is large enough, it just goes on and tries to schedule the next instruction. It's another another descriptor load and moves down all independent instructions from before and moves up independent instruction from after the first user. Can see that we have a read after read dependency between the first sload divert and the second one. At the moment, we just ignore these. I think there's still some room for improvement, but yeah, for now it's just that. So yeah, now the two load instructions are scheduled up. Without building a dependency graph, without rescheduling all instructions, we just check these two instructions, the instructions before and after for everyone, for each one, to increase the distance. And now in the final step, we can also do the same with the image instruction. This again is depending on almost all instructions before and can only move down the two interpolation instructions. This is all. So, and you can see all the time it is adjusting the register pressure, and this lets us stop scheduling when the register pressure exceeds, and this means that we don't have additional spilling costs just by scheduling. This is also our final schedule for this small shader. And let's see what is the outcome, why does it work, or does it work by looking at some shader stats. So this is the difference when compiling like 40,000 shaders with LLVM and then with ACO. We need more SGPR, so scalar registers, a lot more. 10%, almost 10% more register use, and also 2% more vector register use. But at the same time, ACO manages to decrease the spilling by 95% for SGPRs and by 100% for VGPRs. And I think that's quite extreme, to use more registers and at the same time have less spilling. Yeah, ACO has a few less maximum number of waves. But this is something we can decide. So we figured that it seems worth to sacrifice a few waves, a bit of parallelism, in order to increase the distances between loads and users. But this is something the scheduler can decide before scheduling, and it's not the result of some, of whatever the heuristic came up. Or ACO also has almost 8% less code size. I think part of this is because of less billing, but also we do quite a decent job on instruction combining. Yeah, so far, that's from my side, and Bas will now talk about the current state.
Yeah. So initially, we set up this effort pretty much as an experimental effort, like especially with the control flow. We had this idea that LVM might be non-optimal, but we really want to see, like, can we really do better if we apply these ideas? And to do that, we started with, like, hey, we take a single benchmark. We take, like, fragment shaders and compute shaders only, because that's where all your GPU time is spent, and went like, hey, what if we optimize this? And then we generalized from that. These days, you'll see like we still don't support everything, which is pretty much on our to-do list, but we support fragment shaders, compute shaders, vertex shaders. Now tessellation and geometry are still missing. We support basically the same extensions as we do with LVM now, modulo the 16-bit and 8-bit size. I mean, if we want to do them trivial, it's quite easy, but the real challenge there is making sure that like the double rate 16-bit floating point on neither architecture really gets used. We currently support only a limited set of architectures, mostly because, like again, experimentation, we didn't want to go all the way and implement all the legacy support, and we have the same conformance test pass rate as Radv with LVM. Of course, modulo the test for those few extensions we don't support yet. And yeah, Valve has announced this compiler backend like on a GitHub branch somewhere, and with pre-built packages a few months before this, and asked people to test. And we actually got quite a lot of feedback on that, and a lot of like how does it run and which games run and don't run. And we've actually been able to figure out a lot of the bugs, and it's actually pretty reliable these days. And it's been merged into upstream Mesa now, like we expect it to be released as part of the 19.3 release, but it's not the default yet. And of course, one of the things that, like at the start of this presentation, I said like why we did it, and of course you're going to ask like, did we achieve what we wanted to? And like performance is of course one of the key metrics, and we have runtime performance, compile time performance, and I'm showing runtime performance here, delta % change, so less than 0 is bad, more than 0 is good. And I ended up like, what you can see mostly from this graph is that it's all over the place, and typically the effect is not that huge. Like we have a few positive outliers where the effect is really big, like Doom here is one example where really the control flow messed up LVM, and we can do a lot better. There are a few negative examples too, not too much on these slides. If you look at Mad Max, like if you benchmark it, you can get like per scene you can get results, and then one of the scenes is negative, the rest is positive, end result across the scenes is pretty much 0. I think this is a pretty mixed result. Like as I said in the beginning, like cost-wise, maintaining our own compiler backend means we can't really reuse what the AMD folks are developing as backend for LVM, and honestly a few % here and there. Like if we look at a long timeline of a few years, it's probably bridgeable. I mean, it's nice now, but for example, one of the big things that came out when we did the initial testing with Valve is that like the game Nier Automata was significantly faster with ACO. And then if we look at how LVM progressed, like in versus LVM 8, we were 10% faster with LVM 10 latest SVN. They've pretty much caught up with that. So it's not like they're standing still. And I think this is nice, but not a game changer. The game changer is compile time performance. So overall results are basically we compile shaders 3 times faster now. If we look at, so remember Nier is our middle end, and honestly in the Nier results there are some SPIR-V parsing, etc. And we look at our set of stored shaders we do to a compiler runner, then the overall compile time is 3 times faster, but the backend compile time is 7.5 times faster than what we had with LVM. And this, like, the feedback we got from users when Valve sent out the request for testing was really like, they showed us some their benchmark numbers, but not really how they noticed that. But one of the very common comments there was that people experienced way less stutter in those games, and that they really liked that. And I think that is one of the big game changers of this backend. Of course, there's still a lot of work to be done here, to really make sure that we get the full benefits of this. We should make it the default compiler backend, and for that we need to bridge a few gaps, like missing extensions, missing hardware support, and then the real question becomes like, how do you want to switch over in an environment where we can't possibly test every game to make sure it works with the new compiler backend? It's pretty similar to what Intel has with switching over to Iris, and I don't think anyone has found the perfect way to do this, so we still need to work out some plan on how and when to do this. And further challenges are wider adoption, like it would be very nice if we could also use this for Radeon SI. We have more things that we want to do for performance. Like if we look at what optimizations we do, like SSA, our SA-based approach is pretty new, but otherwise we're not doing a lot of crazy optimizations. And one of the things that's really might help us in the backend is alias analysis, and that again can help with scheduling, like can help with your typical backend passes. And one thing that we really need to take a good look at is testing. Our experience with LLVM has shown that the unit tests don't have good coverage of what you really want to work. Game traces don't have good generalizability of making sure that the next game you didn't test yet also works. So what's the best trade-off here? Do we want both? It's really a question here, and we really should figure this out. And that's pretty much the end of our presentation. Does anyone have questions, comments, or complaints? Or
so I have 2/3 questions. I think it's the first one is, could you pull up the GLSL code there? I just wonder, like, if I misunderstood the problem or if I'm misreading the code. Is the problem that those are different I variables, or is the problem that that you doing the same operation outside of the branch? I think it's the latter, and I think maybe you're having int I too much in the. Right. Okay. Yeah. So because that's how I understood their explanation. All right. The second question is. Oh yeah, sorry. Do you wanna?
So to repeat the previous answer, this redefinition of I in the branch in the for loop is wrong, and it's really like that we're executing outside the branch and that they are different there.
Yeah, so the second question was, when you're going through kind of one-on-one the instructions there to reorder under the pressure control, can you somehow end up doing decisions that seem good at the time but turns out being bad because they're preventing other better choices later?
If I understand the question, you ask if this scheduling can prevent further optimizations later? Yes. So actually scheduling is basically the last optimization. So.
But since you do register allocation, spilling first. So since you do spilling first, you don't really want to increase over some threshold the number of registers, right?
I think one of the tricks we do here is like at the time of spilling, like we have a clue like what's the current register pressure, which may be more than we need to have because like we have the 256 limits or like for compute shaders sometimes lower. But there's also tricks like, hey, if we can say like I'm using 55, have a register pressure of 55 now, but I know I get the same number of waves with 56. Like I can put those limits higher, and yes, we make a decision at the spilling point in time, and then if we see a great opportunity in scheduling and it increases significantly, sure, at some point you can't act on it because you already made that decision.
In theory, it also enables you to schedule the spilling decisions. So the spill reloads and so these kind of instructions. But as we actually currently only do SGPR spilling, we didn't find a single shader which causes VGPR spilling this approach. But so these don't need to get scheduled, but in theory it would allow to also schedule these instructions. I think this is not optimal, of course it's not, but I think it is better than to do the opposite, also because the register pressure is low before doing the scheduling. The register pressure is pretty low, and because of that, the spill cost is that low, and it stays that low. Yeah. Other questions, maybe?
Yeah, so I think you just answered my question. So you do take into account threshold. So for instance, if you use 30 register or 31 registers, it does not change a thing from occupancy point of view. But if you use 32 registers and you pass over a threshold, and then the occupancy will be divided by some number. Okay.
Yeah, it's kind of certain bounds. Like, for example, 64 registers allows you to have 4 waves on the SIMD unit. But if you have 65 registers, it's only 3. So you want to really avoid using 65 registers. And that's why we stop at this point. And even maybe insert some shuffling instructions, because a very high register pressure might lead to shuffling needed in the register allocator. That's some move operations to keep the values in the correct registers. But we found that this trade-off is worth it to just keep this amount of parallelism of occupancy on the GPU.
Have you looked, going scheduling again, have you looked into I guess in your case it would be pre-spilling scheduling to try and reduce register pressure beyond, lower than the level it is when it comes out of node? Or are you just assuming that the order the program loaded in is pretty good?
Sorry, is there a question that we should spill more to even further increase the occupancy?
So there may be cases where the order of the instructions that you get coming out of node into your backend, you can actually get lower register pressure than that by doing some scheduling prior to you making you spill decisions. Is that something that you've considered at all? Or are you simply trying to, basically, have you looked into scheduling that tries to decrease register pressure rather than scheduling that simply tries to avoid increasing register pressure?
So some kind of Seti-Ullmann algorithm to lower the register pressure before. Yeah, I thought about this a few times. Didn't have the time to implement it. Not sure if it's worth it. Most of the shaders seem to have a pretty good order before we start to schedule. But yeah, it might help. Maybe we can also do this in near because then also other backends might benefit from it instead of doing it in ACO.
So I think we'll end it here to give everyone some time to leave before the fire drill, whatever. But